Okay, we're back, and we'll continue on the discussion about Bayes' rule on this example of tree diagrams. Let me share my screen. Let's see, I have to share first, then. Okay. Okay. Now there's a red line, the blue line, and the white line, and we are given all those information of. Let's go here. Okay. So we are given all this information about the percentage of the defective. Okay, there's a chance the defective percentage, the chances that tractor will not start. That means this defective of the line 6% for red, white, and blue. There are some numbers, and then percentage of the units that are produced per line, okay, of the entire company. So the space or the world or the universe is about the company production, and there are 3 assembly lines, okay. All the 3 assembly lines in this case consist the space of the factory, okay, and the corresponding items that are coming out from each line. So now we say red for red line, W for white line, and B for blue line. That's the event, and then the D for being defective. So now let's write it out. So we are given 48% of the production of the tractors, of the total tractors in the red line is 48%. The production of the white line for the entire factory is 21%. We have computed this already, and for the blue line is 31%. So we are saying that most likely, I think there are more workers, or there are more factory workers in the red line. Okay, maybe this is the bigger assembly line, most likely, because there are more, almost 50%, almost half of the production of the entire company is coming from the red line, and then the white line is the least one, maybe this is the smallest one, and the blue line is the middle, in terms of production. Okay, now the defectiveness. Okay, so all the tractors coming from the red line, for it to be defective is around 6%. Okay, well, for the white line is 11%, and for the blue line is 8%. So we can see here that there are the most defective percentage is coming from the white line, and they have the least number of people working. Okay, so maybe we can draw a certain conclusion here, or we can make certain observation. Why is there higher defective in the white line compared to the red line, where red line is very small? Well, maybe because the production is small. Okay, if there's one that is defective, then the percentage of that is very high. That could be the explanation. Okay, anyway, but these are all the important information that is given to us. So now the question is, we need to find a tractor, the fraction of the company's tractor that do not start when rolled off in the assembly line. Okay, so that means that we want to see the total defective tractors for all the assembly, for all that is given in the assembly line. How do we know this? Okay, well, we are given already before that, for example, probability of the red. Remember this, where all the red are in the each jars. Okay, then we can consider the red in jar 2 given probability of jar 2. Okay, because we don't have this absolute information, but we are given the information about the probabilities of the relative probability given certain events. In this case of jar 2, and that it is red. And then again, that it is red given that is in jar 1. Probability of being in jar 1 plus the probability of red being in jar 3 and probability of jar 3. Okay? There. So this is a way of computing the absolute probability of an event based on that can be computed from the relative probabilities. So we can do the same thing for the defective part. So for the defective that is not given to us, but the relative defectiveness is given to us. So now we can say probability of it being defective given in the red line and probability of the red line. Now you know already, yeah? Then probability of it being defective given that it is in the white line, probability of the white line plus probability again of being defective given that you are in the blue line, probability of the blue line. Okay? Now it's just a matter of substitution. Finish. Any questions? We're done. This is what it is asking for. The fraction of the company's factor is a company, is the totality of the company's factor that won't roll off, that won't start, but that won't start, that is defective once rolled off in the assembly line. Any questions? Okay, no questions. Very good. Okay, that means everyone understood. Okay, we'll go on the next one. Okay, now this one can be partitioned into an assembly, into this assembly line can be, or this assembly event can be partitioned into like a tree diagram. Okay, now we are putting it. So how does it look like if we represent it as a tree diagram? So this is how it will look like. So you have the absolute probabilities first of red, white, and blue. Okay, all this is the total number of, this is the factory. Okay. So the factories is divided into 3 assembly lines. So the 3 assembly lines like that with the corresponding percentage of the production. So because they are absolute, so probability of red. So this is probability of red. This is the percentage production in the red line, percentage production in the white line, and percentage production in the blue line. Now, given red, what is the probability that it is defective? And like that. So given red, what is probability that it is defective? This is already given to us, right? So that means that not defective is what? Not defective. Yeah, if we assign to be not defective like that, probability of red, so what is that? 1 minus this one, right? 4. That means they will start. So probability of not defective given white, okay, that one minus. Okay. Is this 89? Okay. And probability of Jason, your face seems like you have a lot of problems. Can you tell me?
No, I don't have any problem. It's just that I'm using a phone and
Okay, now,
the
okay,
letter.
okay. So what I'm seeing a happy face then, yeah? It's just that I didn't interpret it correctly. It's the interpretation that's wrong. Okay. Any questions? So that's how, I mean, we are just looking at it in a different way. Instead of base rule, then we look at it in the tree diagram. Okay. Okay, now let's continue. So, well, we are discussing there are three ways for a tractor to be defective. It is made by red, white, and blue company, or blue line. Yeah. Find all the defective ones that we need to know. This one we already copied this. So now we have the defective given the red line, defective given, the intersection of defective and red, intersection of defective and white, intersection of defective and blue. Okay. Now these intersections can be determined, can be shown like this, or we say that we can do it the other way. Probability of red given defective, probability of defective. Okay, we are saying that they are equivalent. Probability of white given defective, probability of defective, and probability of blue given defective, probability of defective. Why are we not using this other set of equations? This other set, why are we not using this? Why we prefer to use that? Sepo, you submitted already your
Yes, sir.
have you submitted your report already?
Attachment report, or
Yeah, of course. I mean, we don't have any.
yes.
Class. I mean, we had, but the time is it's still in Thursday. Okay, can you
That's
answer?
why I managed.
Okay, can you answer? Why are we using this other set of equation, this one, instead of this one? Why are we using this and not this? We are saying that they are equivalent, but we are using that equation, the left set of equations.
I'm not sure, sir.
Okay, it's fine.
I can't seem to think why. No, I can't.
Aborone? Ontlametse. Ontlametse, are you there? Only your head is showing. I think it is just, are you there? You cannot hear.
Sir.
Junior Mudimupelo, are you there?
Yes, sir.
Okay, answer.
I think because of the information that were given.
Yes, correct. It's just did you take this course again, or you were my student before, or what, in this course, or no?
It's the first time I take this module, but I've been a student before.
Yes, I know you were my student before, but this module is your first time.
Yes, sir.
Okay, you tried to avoid it last semester, the other year, yeah?
Yes, sir.
Okay, now there's no escape. Okay, so yes, that's correct. So we are going to use this equation to the left, this set of equations to the left, because that is what we know of. Okay, if we take the equations on the right, I mean, that's what is given. The information is given to us. But to the right, we don't have the probability of the defective because that is what we are looking for. They are equivalent, yes. But on the right-hand side of the equation, of the right-hand set of equations, we don't have those information. Okay? Okay, let's continue. Now, there. So we use it. I mean, exactly the same as I've written. This is the probability of the defective tractor. The entire probability that the tractor will, I mean, the probability that the tractor is defective when it rolls out of the company. Okay, the total defective tractors for the entire company, given the defective from the red, given defective from the white, and given from defective from the blue line. Okay, now the next question. What is the probability of the tractor that it is a defective tractor that's coming from the red line? Okay, so the tractor is defective, yes. So now, given that this is defective, now what is the probability that it is from the red line? Okay, well, okay, we know from the equation that probability of red intersection of being defective, okay, we can write it as probability of red given defective and probability of defective. Can we use this one now? Or which one we want to use? We can use probability of defective given red and probability of red. Which one we want to use? Well, we want to use this part because this is the unknown one. This is what we want to solve. So divide this in the equation, divide this one to make this one go down. So we get this. Okay. Well, sir, we already have, how can we try to avoid the probability of the defective? Why now we use it? Well, we know it already. Okay. We have computed this, so we can use it. Okay. How do we use this? Well, we use this because we want to compute for this information, and then that's why and then now there's another way of writing this. Now we use this one, this part, because that is what we know of. Probability of D defective given that it is from the red line, probability of it, probability of the production, absolute probability of the red line, probability of defective. Finish. We know this, we know this, we know this. We can compute this. Understand? Okay. So now let's continue. I think it's clear. So everything becomes clear now. So in this case here, we have a particular output B. Okay. In this case, there are many outputs, B1, B2, B3 to Bn. One of the possible outputs of B is Bk. So we want to know what is Bk given A, where A is also another event. Okay, so now we say that the A is dependent on particular information about the B event. The A event is dependent on a particular B as a component of B that is Bk. So we can just rewrite like this in terms of the base rule. This we know. No problem. Now the problem is here. So here we say that is there another way of of writing the absolute probability of A, especially in this case that A is dependent on a B event, a BK, a subset of B, which is a BK event. Then we have to go through all the subsets, all the components of B. Probability of A given that first component, B1, probability of B1, like that, plus probability of A, same A, component of B2, probability of B2, like this, and so on. And so we write it like this because the event A is a dependent probability. It's not straightforward to compute for us the absolute probability of A. Okay? Any questions? Where I'm just trying to emphasize this part, that given A here, you can write it in terms of the subsets of the given event. Now, let's continue. So, okay, let's have another example here. And we finish. Okay, that is the last two slides, and we will finish our discussion. Okay, what time is it now? It's 15 more minutes. Okay, can someone read this? Right, Mudise?
Yes, sir.
You read.
Only 1 in 1,000 people have rare disease A. TP equals to 0.99. FP equals to 0.02.
True
If one
positive.
randomly tested individual.
Hold on, Mr. Bright. TP is the true. Yeah.
Okay, true percentage equals to 0.99. False percentage is equals to 0.02.
Positive.
If
False
one
positive,
randomly
positive and false positive.
True positive equals to 0.99. False positive equals to 0.02. If one randomly tested individual is positive, what is the probability they have the disease? Label event A equals to has disease, A not equals to no disease, B equals to positive test result. Examine probabilities. Probability of A equals to 0.001. Probability of A not equals to 0.999. Probability of B given A is equals to 0.99. Probability of B given A not equals to 0.02. B given this ratio.
Probability of B given A, like that. Are you done, Mr. Bright?
I have read.
Okay, very good.
I'm done. I have read.
Okay, although I don't know when you finish already, but yes, you're finished, yeah? Okay, so now let's okay, the question here is that somebody positive, okay? And what is the probability? We want to know that this person, we can write down all the possibilities, okay? That A has a disease and it turned out positive, or maybe you say positive result is B, okay, and he has the disease and come out with a positive result. That's one. Or we can say that probably this is given already. Yeah, this is given. Okay, and that he turned out positive, but then he has no disease. This is the scary part. Somebody will turn positive and actually he has no disease yet. Okay, but it happens. So we are trying to look at the possibility that this one turned out positive, he has the disease given. So now we need to ask the question, okay, that somebody turned out positive indeed he has the disease, and then somebody turned out positive, but that somebody really does not have a disease. This one is what we want to know, and this one also what we want to know. Because oh, I'm positive of COVID, for example. What is the probability that I'm really positive? Or because here it may be RT-PCR, maybe it's very accurate, but the rapid test, the rapid test, you turn out positive, then there's still a probability that it was a mistake. Okay, so this is the one that we want to know. When you turn out positive, what is the probability that indeed you have the disease? And when you turn out positive, what is the probability that indeed you don't have the disease? I mean, but that you don't have the disease, not indeed, but you turn out positive, but you don't have the disease. Okay? So from here, you say a person is positive, and then B plus is a true positive, B minus false positive. Okay? Here, the person has no disease, then it turned out true positive and false positive. What does false positive here, true positive here? That the person really has no disease. You get it? Questions? Okay, let's just write out the equations. So now, if you want to know this, what is the probability somebody turned out to be positive, but he has no disease? This is what we want. This is the most interesting part. So to write the probability, how to write it? How do we write it? Well, we can write it as what? Intersection divided by what? No disease. Is that correct? Let's just check it. It is based on the given. This is the given event. So it will be, I want to see that, given event B. So let's just say that. Sure. Okay. So on the top, what we can do is that probability of, we don't solve for this one. We don't say probability of A give A0 given B, because that is what we are looking at. So now we use B, probability of B given probability that it turned out positive and given that he doesn't have a disease, and probability that he doesn't have a disease divided by probability of being positive. Okay, but are we given the probability of the being positive? No, we are not given, but we are given all the possibilities of being positive. Positive with the disease and positive without the disease. So now we can rewrite this as probability of being positive given that he has no disease, probability of no disease divided by, how do we write this? So we write it as the probability of being positive given no disease probability of no disease, plus what's the other probability? Probability of, again, positive with disease, because that's the other case, probability of with disease. Finish. Okay, it's just a matter of substituting values. Now, what is the value of this? The first term, second term. Probability of no disease. This is 0.999. Probability of B given no disease, 0.02. So this is also 0.02, and this is 0.99. And probability of B given with a disease, 0.02. 0.99 multiplied by probability of A, 0.001. Okay, what's the answer? Somebody compute. What's the probability of someone turning, what's the probability of someone diagnosed as positive, but that person really has no disease? That's the question. Can somebody compute? Moise, can you compute?
Yes, sir. I
Okay.
don't have a calculator with me, sir.
No computer. Do it by hand. Do it by hand. Is it difficult? Can you multiply it by hand? Yes. Let's do it together. Okay, we're running out of time. Sepo, can you multiply it? Come on, I don't need to call you to multiply it. Can you just do it? Okay, come on. Okay. Nobody wants to compute. Okay, let me be, 0.999. Okay. Plus, what is this now? 0.99 times 0.001 equals, now that's the denominator. So 1 divided by that, 0.020971, 1 divided by 0.02097 equals times 0.02 times 0.999 equals. How come? Did someone calculate it?
0.956.
0.957. Okay, so because of the given records, it says here that if you turn out positive, most likely you don't have the disease. So you don't worry about it, because here we say there's a small percentage of people with no disease that are turning out positive. Okay, what is the percentage of the person turning out positive and indeed he has the disease? Well, 1 minus this, right? What is the probability of turning out positive and person indeed has the disease? Because there are only two possibilities here, with or without the disease. So complement of this is what? Come on. 394 there, 0.043. Okay, so that is a probability when you turn out positive and indeed you have a disease. It's a small percentage. Okay, that means the disease is very rare. Okay, let's check. There. Is this 1.4? This is 0.43. Well, it's just our calculation, 0.097. Okay, let's look at their solution. Okay, probability of a positive, given that you have the disease and you turn out positive. You have the disease, you turn out negative. We know this already. You don't have the disease, but you turn out positive. Oh, okay. I have a different interpretation here. You have the disease and you turn out positive, and you have a disease, you turn out negative. Okay, so this one we're given. Now this is the absolute percentages. And now if we look at the intersect, what is this now? Intersection. What is this that how do we calculate this? What is this intersection? So that's B given A, probability of A. We just multiply it. That's this one times this one. So 3 more, 1, 2, 3. So 3 zeros, yeah, that's correct. Now, this one is equal to probability of B given no disease, probability of no disease. We just multiply. We just multiply this one with that one. The same thing, this one multiplied by that one. So now, this is the intersection of without the disease and but positive. So it's quite high compared to this one, positive but with the disease. Now, probability of you turning out positive and indeed you have a disease. So this is very small. And so probability of you reading positive but you don't have the disease, then it's a complement of that. It will be 0.3, sorry. That's 3, 9 minus 4, that's 5, and 9. Okay? So there's a high probability that when you turn out positive, that you don't have the disease. Any questions? Okay, it's right on time. And that's the end of today's discussion. Any questions? Okay, I'm going to give you exercise number, we skipped number 5 because it's a game that I want to discuss further. But given the time, we don't have to discuss the game. Now we'll do the yes or no, the yes or no playing tennis information. Okay, just play around with the equations, then you will find the solution to that problem. So everything again is manual. So you just scan or picture your computation and then paste it into the Word document and upload it. I mean, make it a PDF and then upload it. Okay? Any questions? Please, I encourage, of course, many of you can work together and encourage you to work together. But I also would encourage you to write your own solution by yourself, because this is supposed to be the exercise for the long test one. I'm sure if you just copy from the other person, you need to copy again for that other person during the long test. Okay? If you don't get lucky, you're not sitting beside that person, then you won't get anything. So it's better for you to really do it yourself. Okay? Okay. So Thursday, we'll have a lecture again on Thursday. So this coming Thursday, there will be 3 laboratory exercises. Okay, to submit. 1, 2 for decision trees and 1 for the Bayes rule. Good luck for the long test one. Long test one on Friday. I mean, do it now. Do it do it now, then you'll finish it. It's just for one setting. Each laboratory session can be done in one sitting. Questions? All right. Okay, no pain, no gain. Yeah. Okay. See you guys. Bye. See you Thursday.